This is a presentation that I gave at the Lisbon-Lausanne Workshop on time in the foundation of physics, and I thought I will make a quick video out of it. For those that don't know me, I work together with Professor Cristina Dalla on a project called Assumptions of Physics that aims to find a minimal set of starting points from which the laws are derived. The project consists of two main efforts. One is we call the reverse physics, which we start from the laws and find physical assumptions that provide equivalent formulation to understand better the content of the physical laws. And then another effort that we call the physical mathematics that starts from the physical idea and carefully encodes them in formal definitions to rederive the familiar mathematical structure so that we have a sort of a very precise way to proceed with the foundations of mathematics and physics. So in this talk, I'm going to be talking about the nature of time, and the two main points is that the mathematical structure of time, that is the real number with the standard topology, can be understood as coming from an idealized operational model of clocks. So the mathematical structure is not really describing a time as sort of as a physical entity, but it's actually a model of how we measure time. It's a model of our instruments, of how time is defined operationally. And then what happens is that as time resolution increases, this model must fail because it's very idealized and needs to be replaced with a more realistic account. So the idea is, again, it's not that we are going to find a better nature of time as something that exists outside of us. We just need a better model of how actually our clocks function and how we do define time operation. So the talk is divided into three parts. In the first part, we're going to look at the question of what is time, and we're going to look in general what it means to define something, what are the challenges in providing good definitions, and we'll talk about the role of operational definition within science. We're going to see how experimental verification imposes already a mathematical structure through topology. We're going to talk about the role that synchronization has in defining time. In the second part, we're going to take this sort of nebulous discussion that we have in the first part, and we're trying to actually make a formal model out of it. So we'll see how we can take some concepts and make them a formal mathematical model, and then so that we can talk about it more properly. And so we're going to talk about the sort of the metrological and logical structure of clock. What does it mean to define these things in a precise way? And we're going to find a set of necessary and sufficient conditions for continuous time. So such that a set of necessary and sufficient conditions under which we can pretend we can model time as a real number on a real line. And then, once we've done that, we're going to discuss in the third part the inevitable failure of time ordering of this model. And basically, the conditions that we have for continuous time are untenable at Planck's length as we make this time more and more precise. And what happens is that time ordering itself must break down. So it's not that we don't have real numbers, we have a more complex structure, but we still have time ordering. No, it's time ordering itself that needs to break down in some fashion. So, okay, let's start with the first question, what is time? And one might think that this question is hard because time itself is a difficult concept to understand. And so, if that's the case, if this question is hard because time is hard to define, then it should be true that defining anything else should be easy. So let's start with a different question, like what is a table, and see if that is actually as easy as we think it is. So if we look online for a definition, a table can be defined as an article of furniture supported by one or more vertical legs and having a flat horizontal structure. Okay, well, what about this thing, right? This is a flat surface, but it does not have legs because it's being held from the ceiling. In fact, this, I suppose, it's something that you can lower up and down so that you can have or not a table. So the table can be up and out of the way. So this would not be a table according to this definition. And let's look at this. This has legs and it has a flat horizontal surface, but, well, it's a flat surface, but it's not horizontal. So this would not be a table. And if we look at this, these are Lego. This is a Lego table, right? So this is not an article of furniture, but we still call this thing a table. So you might say, okay, well, one other way of defining a table would be as a function, right? So a table is something, it's a flat surface on which we can put stuff, right? But then you could argue that the back of a car is a table because you can put stuff and you can probably go and work in a pinch if you really need to stop and you have nowhere else to go. Or maybe you have this thing that if you can't really understand here what it is, it's a transparent table with a lot of money in it. And you can imagine that if you went through custom and said, oh, this is just my table, they might have a problem of considering that just a table. Like you could fill it with gold and diamonds, that the custom people would not like that. So they probably would object to you just saying, oh yeah, this is just my table. So what happens here is that at the end of the day, it's really the what is part that it's elusive. Like defining something is hard. And why is it hard? Well, because before giving a definition, we need to say what is the purpose of the definition. And different purposes might warrant different definitions. So if you are in a tax context, in a legal context, in a technical context, the same word might acquire different meaning. And it's hard. You need to be clear in what is the purpose of the definition. And then you also have to be clear in what are the prime elements that are allowed to be in the definition, because any definition is going to define something in terms of something else. So what are the something else that are allowed to be put in the definition to have a definition that is acceptable? So for example, if we had to define time in math, we want a formal definition. And a formal definition in math is some set with some property. And how do I know that? Because that's all well-defined math objects are. Or if you're doing category theory, maybe you have something different, but that's basically the point. You have some foundational mathematical objects, sets, and everything is a set. And so you have to define anything else in terms of sets and properties of sets. So, for example, you might say that in math, time is a variable that can be used as a parameter for the evolution. And so you have a set of possible values and some structure and so on. Now, in philosophy, you might look for something different. The formal definition might not be enough. You want some ontological definition, some intrinsic feature of reality. And I have to tell you that I don't quite know exactly what philosophers consider well-defined, but I found in some philosophical paper that time was defined as a non-spatial continuance in which event occurs. So it seems to be that this definition, for some cases, a philosopher would find acceptable. Now, are these acceptable definitions for us in physics? Are these useful definitions? Well, the answer is no. If I'm in a lab and somebody tells me, oh yes, time is a variable that can be used as parameter for the evolution, well, that doesn't tell me how do I measure it, how do I do anything with it at an operational level. And the same thing if I give an ontological definition. I need to be able to do something in a lab to be able to characterize these things, and these are not enough. So what is it that we actually need in physics? Well, when we are in a lab, we need an operational definition. We need a way to define through some procedure how to produce time, how to measure time, and this is for any object that we need to be able to characterize it in a way that I can tell my friend somewhere else and he's able in his lab, he has enough context to be able to replicate what is it that I'm doing. And once we have this, we're good. So that's what it means to be well-defined in physics. The ability to be able to give a set of instructions to somebody else so that he is able to reconstruct what is it that we're doing and duplicate what we're doing. So what is time in this context? Well, time as an operational definition, time is what is measured by a clock. And this is an operational definition in the sense that it tells me what to do. I want to know what time is it, you go look at a clock, you need a clock. Now, of course, this seems to be just, kicking the problem one step, and we now just have to say, what is a clock? And of course, somebody will say, well, a clock is just what measures time. and now you have a circular definition, and this is completely useless. Now, this is not useless just because it's a circular definition, is that saying that a clock is what measures time, it's not an operational definition of a clock. It tells me what a clock is doing, but it doesn't tell me how to produce a clock, right? An operational definition has to tell me how do I create one of these things. And so this is not a good definition because it's not an operational definition. So what is an operational definition? If we want to say, what is a clock, and answer with an operational definition, what can we say? Well, we can say that you can use the sun as a clock. Or you can use the seasons as a clock, which is still the sun, in a different form. Or we can use our heart by measuring the pulse, the number of pulses. That can be used as a clock. Or a bucket of water with a hole is used and was used as a clock. Or a pendulum can be used as a clock. We can count the oscillation. It's pretty regular. And all of these, you can get a set of instructions on how to build these. They have operational definitions. So these are good definitions of clock. They're good. But we still haven't said what a clock is, right? We just gave a bunch of examples of clocks, which is a step in the right direction, but it just doesn't tell me what is a clock. If I had to create a new clock, what should I do, right? And here the answer is, again, trivial. A clock is anything that can be synchronized to other clock. And this is exactly how how the history of time, of how we created more and more better and better clocks has worked. We had rudimental clocks. Somebody creates something better, and then that something better can be synchronized to the other, and then you get better and better and better resolution. And all of these things can be synchronized. And synchronization is operationally defined, right? Every time that this click 5 times, this click 1 time, so you define some kind of ratio, and you can synchronize them and say, okay, now this I start at the same time, and then I know how the clocks proceed in both cases. So that's nice. And so the idea is really that our ability to synchronize clock is what gives us the idea that there is one time. Right? If we were not able to synchronize this clock because every clock did something crazy, we wouldn't have the sense that there is one thing that all these clocks are measuring. And so the examples are important because they serve to jump stamp the process, right? In the same way that, to learn what is a fruit, we're given a bunch of examples first, and then we sort of generalize and find commonalities. And then here is the same. We start with rudimentally the idea of clocks, so we create more and more well-defined clocks, and all of these things share the notion that they can be synchronized. Okay, so we solved the problem of the purpose. We need operational definitions. And now we need to answer what are these prime elements, especially if we want a formal definition of these things. What are the prime elements that we're allowed to use in our formal definition? And here is where we have, in the Assumptions of Physics project, we have sort of a generalized way of how to do it. And our primitive for everything is the idea of a verifiable statement, an assertion that can be experimentally verified in a finite time. So if the assertion is true, the test is successful, and every time that the test is successful, that statement is true. So for example, the mass of the photon is less than 10 to the minus 13 eV is a verifiable statement, because we can go and measure the mass of the photon with greater precision. At some point, we get that cutoff, and then we say, okay, this assertion is verified within that bound. But saying that the mass of the photon is exactly 0 electron volt, that's not verifiable because it would require infinite precision, and we cannot perform infinite precision measurement. All our measurements have always an error bar. But it is falsifiable in the sense that if we were able to measure at some point there was a cutoff on the lower bound, that the mass of the photon has to be greater than something, then we would be able to exclude 0, and then we would have falsified the statement. So part of the framework is really to understand and classify these types of statements. But the idea is that These statements are taken as a unit. So the syntax, the semantic, the structure of the statement, how the test actually perform and so on, this is not formally specified further. In the theory, you basically say, there are these things that I can verify, and I guarantee you that there are tests of how to verify these statements. But then the formal theory does not know more than that, because providing these extra element formally is basically impossible. Creating a really rigorous formal operational definition is not possible. At some point, there is a sort of good enough in science that it's sort of pragmatic and not mathematically rigorous. So, for example, whether a specific statement is experimental, verifiable, or even well-defined may depend on a context. That depends on the premise, on the type of visualization that we're doing, the type of theory that we're trying to create. And even just something like the mass of the electron is 511 plus or minus 0.5 keV can have a different role depending on what we're doing. So if we're measuring the mass, then this is a verifiable hypothesis. It's something that it could be true, it could be false. We go and measure and see what it is. But if we are doing particle identification in a particle detector, then we assume this to be true. So that if we see a charged particle with around that mass, we're going to say, oh, that's an electron. Right? We're not measuring the mass of the electron, we are using the fact that we have measured the mass of the electron to be that value to then identify what particle it is. So that statement plays different role in different contexts. And that shouldn't be a problem, that shouldn't be surprising, but it basically makes it impossible to define a single perfect way of what an electron is, what that statement means, if it's verifiable or not, if it's always true or always false, and so on. It makes it very, very hard. So just to give you a sense of how this formal structure works, because it's something that we're going to use later to formalize some of the ideas about time, we start with a set of verifiable statements that is generated by a countable set, in the sense that countable tests is the most that we can check. And these are closed under finite and countable OR, because these are the operations that preserve the fact that we have verification. If you make a finite AND of verifiable statement, you still get a verifiable statement. If you make a countable OR of verifiable statement, you still get a verifiable statement. Now you can close this also with the NOT and countable and OR, and you can get a Boolean algebra. This is actually the type of structure that then was used for probability theory and so on. But these are the statements. If we close under those operations, we don't have verifiable statement anymore, but we still have statements that are formally, in line of principle, associated with an experimental test, whether it terminates or not. And so these are still a logically sound statement because they're still grounded in experimental verification. And within this theoretical statement, we found what we call the possibilities, which are the statements that represent experimentally distinguishable case. So in our case, the possibility would be the exact moment in time. And so if we know that an event happened at exactly 2 seconds, we would know exactly which statements were true and which statement would be false within the whole theory. And now this is like a nice toy, but the point is that this maps very, very well to the math that we typically use. So the possibility will map to a set of points in some space. The verifiable statement map to the open sets of the topology, and the Borel sets map to the sigma algebra. The Borel set represent the theoretical statements and are the sigma algebra that is generated from the topology. So the point of this, regardless of whether you understand what these pieces are mathematically, the point is that we can make a precise map between the physical concepts and their mathematical representation. And whatever we are representing here are essentially statements and their logical relationship. And this allows us to translate all the proofs that would be mathematically abstract into physically meaningful language that essentially all have to do with experimental verification. So we have a nice layer of math that is very physically motivated, physically meaningful, and we can understand precisely what all the relationships are. And this is the type of rigor that we want to have in physics, and we would like to sort of redo a lot of physics in this way, because then we can make more precise statements about the math, but also the physics, and conceptually the philosophy of what these things actually represent in reality. Okay? So the point is that from our point of view, a physical theory is fully specified by a countable set of verifiable statements and their logical relationship. And these are going to give us the set of points, the topology, the sigma algebra, on top of which then we can create all the other geometrical, probabilistic, measure theoretic objects that we have in physical theories. And so all mathematical objects that we use in physics, this is the punchline, all the things that we use are ultimately identify statements and their relationship. So if we have a geometric space, we're basically characterizing statements about position within volumes and how these volumes relate to each other. And if I find something in this volume, it cannot be in this volume, and so on. Okay, so we basically addressed this problem. We want a definition that come from an operational perspective, and our building blocks are this idea, this notion of verifiable statements, something that we can actually say yes or no, and we can verify that the statement is true in with an experiment, which again is an operational concept, in a finite amount of time. So now the idea is that we want to create a model of time that starts with this idea, that starts with the metrology, with how we measure things, to be able to create something that is formally well defined. So how do we do that? So how do we formally model a clock? We start with the idea of a reference that is a tick of a clock, that is something that allows us to distinguish a before and an after. So if it's a reference, right, this is a tick of our clock, something can happen before, something can happen exactly on the reference, something can happen after, or it can also overlap. It can be both before and on the tick, or it can be on the tick and also after, because whatever we measure, both the tick and the thing that we measure is going to have some extent in time. So all these cases are in principle possible. Okay, so how do we model this idea of a tick of a reference in terms of our verifiable statement? Well, we say that mathematically a reference is a triple of three statements, before, on, and after, such that before and after are verifiable. I can say, oh, the event happened before the tick, or it happened after. And then we want that the references has an extent, so there are some cases the on is not an impossible statement, it's something that can happen. And then if something is not before nor after, then it must be that it's on. So in this notation, not B and not A is narrower, implies on. And we also want to say that something is before and after, then it's on. So in this notation, we say that before and after is narrower, is a narrower statement, it implies on. And so the idea is that if you look at the truth table, these 6 cases are the one that are possible. These 2 cases, the one that would correspond to the extra 2 lines, are impossible, are discarded. They are not consistent with the idea of a reference of a clock. Okay. So a clock then is just a collection of these references, right? We basically can imagine that there are all these ticks, and we're able to check whether something is before or after any of the ticks. We take all these statements together in a bag in the same mathematical structure, and that's the formal model of a clock that we would have. Simple enough. So now imagine collecting the references of all possible clocks into a single logical structure, right? All the ticks, all the before, after statement, you put them all in the same structure. And then we ask, what are the necessary sufficient conditions such that this structure, that all the ticks of all the possible clocks identify a point in a real line? So that the possibilities that these statements identify are ordered elements of a real line. That's the question that we're trying to understand so that we have a good and formal model of clocks. So intuitively, we can think that we would need a bunch of clock at higher and higher resolution, all perfectly synchronized and so on, right? So that should basically be the thing that we're going to expect, and that's what we're going to find. But we have to make a formal model of it. We actually have to do the work. Otherwise, all these are just words that I'm saying. If I can't show it mathematically, I have nothing. So we have to do it. So how do we do it? Well, first of all, the first requirement that we find that we need to have is the idea of a strict reference. As we said before, the thing that we are measuring may not always be before, on, or after. They can sort of overlap. And for a strict reference, that cannot happen. Everything is either before, on, or after. So there are only three possible cases for a reference. Nothing else can happen. And this, you're basically assuming that the extent of what you measure is very small compared to the extent of a reference. So our ticks have sort of a wide resolution. You can't really resolve inside. And what we're measuring is much smaller, so you can always say, oh, it's either before and after, because the cases in which you're really overlapping, they're small and they happen very rarely, and we can disregard them. Okay, so that's one thing about one specific of each reference. Each reference has to be like this, but the idea is that these references sort of be to have logical relationship between each other. And so if we have multiple references in general, right, even if they're strict, we could have 8 cases, right? We could be before, we could be before on, we can do before and after, and so on, right? We could have all 9 cases. Of course, this does not really work if we actually expect to recover a linear order. We can't have all these cases, right? So what we need is these references need to be somehow defining, be aligned, right, in terms of before and after, right? And so, for example, here we see that if something is before a reference number 1, it also has to be before a reference number 2. And if it's after reference number 2, it must be also after reference number 1. So we have these 4 cases are now excluded. We only have these 3 cases. But what we find is that this order relationship between references is actually too restricted. We need something that is a little bit looser than that. And what we can see here as a hint is that these boundaries seem to be ordered themselves. So if something is before 1, then it's also not after 1, and it's before 2 and not after 2, right? So these lines of division are ordered. And so the idea is that those are the things that we have to have an ordering relationship with, not really the references themselves, so that we can in principle have overlaps. So we come with the idea of the second requirement. So these are our references are aligned, and mathematically 2 references are aligned if the before and not after statements can be ordered by narrowness and implication. So in this case, for example, even if we have an overlap, we see that before 1 implies before 2, which implies not after 1, which implies not after 2. So we have this type of ordering in terms of our narrowness implication logical relationship. And so this turns out to be the right characterization that we need. We need all references to be aligned with each other. But it's not enough. It's not enough because we need to be able to fill the whole region, because if we have 2 different references that overlap, we can't say that one is really before the other. So we can't really resolve the linear order, and that we wouldn't be able to recover the real number if we didn't have the linear order. Also, if we have references that are well ordered and there is space in between, we need to be able to resolve that space in between, so we must be able to put other references inside to be able to make the right resolution. So we come with this idea of refinable references, and these are sets of references where we can address these previous 2 problems. And there is sort of the mathematics of this, you can go and look at it. I'm going to leave a link of the book inside the notes, but Really, the idea is that if I have an overlap, I need to be able to find a reference with a smaller that is able to resolve that overlap. And if there is a space in between two references, I need to be able to stick a reference in between. And so you do lots of pages of proof and calculation, and what you find is a theorem that tells you that these three conditions are enough to create a linear order. So to define an order sequence of instant, the references must be, and that's a necessary and sufficient condition, they must be strict, so that every event is strictly before, on, or after the references, nothing extends over the tick. They are aligned so that they share a notion of before and after. The logical relationship between statements are sort of well ordered in terms of implication, and they're refinable because the overlaps can always be resolved. If we have these three things, then we have a linear order. Now, if additionally we say that between any two references we can always have another reference, then that linear order is the order of the real number. If instead you say that you can only have finitely many references between any two references, then you get the integer. So it's very nice because you get these three conditions to get a linear thing, something that has a linear order, something is strictly before or after the other, and then depending on of these extra conditions, you get the notion of real number. Now, it has to be said that for time, these conditions are idealization. We're not going to expect that these conditions hold. So let's look at the last part of the presentation, the inevitable failure of time ordering and how time cannot be a real number. So how does this model break down, and what are those conditions that we have mathematically? What do they mean physically? Well, the ticks of the clock have an extent, and so do the event. So the references are not strict. And if we don't have strict references, we're not going to have a linear order. Moreover, clocks have jitter. We can't achieve perfect synchronization. So if we have two clocks that are ticking, we can't really be sure that the third clock is exactly at the same time of the third tick of the other clock. So there is going to be some jiggling around. And that means that it's not always true that whenever something is before this is also before this, when something is after this is always after this. And so the references are not aligned because you could have different cases because of the fact that you can't achieve perfect synchronization. Moreover, we cannot make the ticks as narrow as we want. Right? At some point, you require more and more energy to scan at a higher clock resolutions, and so at some point, this is not going to work. So it's not true the references are unrefinable. And note that you just need one of these things to fail to not have time ordering, and we make good arguments that all three must fail. So if any of these three fails, and we think that all of these three are fails, we don't have a consistent ordering between clocks, right? We have no objective before and after between the clocks. Sometimes this is before, sometimes this is after. We can't really tell. It's sort of we are rolling the die there. Now, in relativity, different observers measure time differently, but the ordering the same. Like if something is in the light cone, it's before and after for everybody, right? This is what we expect to fail. That a small scale, the before and after, even if it's in the light cone, for small resolution, is not going to be objective. It's not going to be shared. We're not going to have a shared notion of before and after. The smaller time we have, the more fuzzy these things are going to become. So again, the idea that a better understanding of a space-time means creating a more realistic formal model that accounts for those failures, right? So we shouldn't be thinking of, what is actually there? What is the fundamental structure? What is that physically happening? No, we should just look at our clock and understand what are the type of idealization that we're making in this process, and try to make models that actually account for that are a little bit more sophisticated. And I can tell you it's very hard because we take those things, we take time as a primitive, and we take clocks as created by by somebody else usually, and the people who do metrology, right, they avoid these problems, right? They want to have a good clock, and a good clock must satisfy those things. A good clock, we need to be able to synchronize. We need to have a sufficiently narrow clicks so that we have good resolution, right? So the whole point of metrology is to avoid those problems, right? And we need to do the opposite. We need to embrace those problems, understand exactly how they are, what they are, so that we can give a better mathematical characterization of them. So that's an interesting thought. So now the following question is, well, if those models fails, what should we use? And again, this is hard to say, but we can argue from necessity. If you see, a lot of the things that we do here are trying to argue from necessity. We must have verifiable statements. There must be ticks, and we must be able to say that something is before the tick and after the tick. So what can we argue from necessity is that we need a lack of order at small scales because we saw that it fails, but we still need an order at large enough scales. We need to have a structure that sort of does this weird thing, that if things are close enough, you can't say they're before and after, but if they're far apart from each other, you can. And so this is kind of a toy model, and it's really a toy model because it's discrete, and this is not going to be at all representative. But the idea is here that we have these are sort of the instants in time, and these are the time order relationship that are defined. So we can know that this is before this, and that these two instants are before this. But we can't say whether this is before or after these two. That's not defined. And here is the same. This is before these two, and this is before this one. Now, if these are the only ordering relationships that are defined, you see, we can move this in front of this or after, and we still have something that is valid. We still have something that respects the before and after. So the ordering between these two things is not defined, but the order between things that are far apart is defined. So we might expect to find something like that, and something like that is very different structure of what we currently have in our normal model. And one of the issues here is that the way that we distinguish things experimentally, so the topology, it seems to be linked to how precisely we want to be able to distinguish. That is the geometry, right? If things are far apart, we need to be able to say that there is a before and after, and if they are close apart, they're not. And here is that the current mathematical tools have a hard division between them. There is a hard division between topology and geometry. Topology knows only about sort of the nearness of things, but it does not know about the geometry. So if you take a manifold, it's scale invariant. If you zoom in on a real line, it always looks the same. And we need to have something that is exactly different, right? That the closer we get, the smaller things get, the more the topology has to change, because our experimental verification is going to become like less and less precise. So these are things we don't currently have in mathematical models. So this suggests we really need different mathematical tools to handle these cases. So now this type of reasoning may seem to contradict, and it does contradict, the expectation of many that may think that time is simply discrete at the smallest scale. And the issue is that this idea that things become discrete, that the continuum is like the discrete marble point, it's basically a problem. This idea is very common in physics, but it's flawed, and it has been abandoned by the mathematical community because it just doesn't work. So one of the things that I want to dedicate the last few minutes is actually debunk this problem. So to understand exactly why the discrete and the continuum are different from a topological sense, and also then from an experimental verification sense, and therefore why they're physically different, that they're completely two different things. So let's look at the topology of the reals, the topology of the integers based on this idea of references, right? So what does it look like? What does a reference look on a topology of the real? Because this would be a reference. So we would have a before and an after, and these are open sets. They're open intervals. So the reference is a closed set, so it must have something inside. For the integer, we have the same thing. We have an open set before and an open set after, and there must be something inside as well. We said that their on must not be empty. Now, if we get another reference on the reals and we make it closer and closer and closer, what happens is that because these are open sets, if these do not overlap, there is always going to be some space between them. Right? There is always going to be space between two references that do not overlap, and this is what makes the continuum. This thing topologically is stated by saying that the space is connected, that it cannot be divided into two disjoint open sets, right? There is always something in between. We can't break up two parts. Now, on the integers, we start with our answer, we make it closer and closer and closer, and when we are close enough, you see, here there is nothing in between. This reference really comes before this. And so the whole space is disconnected. It can be divided into two or infinitely many disjoint open sets. And again, the experimental verification here works differently. How does it work differently? For the integer, all contingent statements, all the statements that could be true or false, are decidable. So any statement in the topology of integers, you can tell in a finite time whether it's true or false. I have an integer of integerly many coins in my pocket. I can tell you whether I have 3 or not. Like, those questions are always answerable in a finite time. Now, for the topology of the reals, all the contingent statements are not decidable. You can't have a statement that you can both say that it's true or false in a finite time, because you would be able to separate the space into two different things. The space would not be connected. So what happens is that any verifiable statement in the reals is not falsifiable. You can only say it's true in a finite time. We're never going to be able to say that it's false in a finite time. But on the integers, any statement that is verifiable, it's also falsifiable. You can tell whether it's true or false. So these two properties, if you start with the integers and you keep putting points inside, that property always is maintained. You always have everything decidable, everything is decidable. So it's not going to happen that in the limit, when you have infinitely many, you're going to have some statements that now somehow they turn out to be not decidable. So they're really two different spaces. So, okay, to wrap up. Physical well-defined object must be defined in terms of operational definition. And this is something different from math and philosophy. Physics needs these type of things. So mathematicians might get frustrated because operational definition cannot be made formally precise, right? But these are the things that we need to have. And the primitive elements are going to be these verifiable statements, which are typically idealized and left formally undefined, right? We measure that the mass of the electron is less than a certain threshold. What exactly is the electron? What exactly is the mass, right? It's the thing that we go and test experimentally. It's that mass. Right? We're not going to formally define it more than that. And so physical theory is fully characterized by the logical relationship of countably many verifiable statements, because countably many verifiable statements is all that we can test experimentally. So we have accountability fixed for us by just our ability to do experimental verification. Time is what measured by a clock, because that's the operational definition. And the main feature of clock is that they can be synchronized with each other, which again is an operational definition. So if you can find a process that can be synchronized with other clocks, well, good for you, you found another clock. Clocks can be formally modeled by a set of ticks that are experimentally defined before and after. And we have recovered that time is a continuance under suitable idealized conditions, that all clocks can be firmly synchronized, that can reach arbitrarily small resolution, and so on. But the idea is that we should not expect this assumption, the assumption required by ordered and continuous time, to hold at the smallest scale. And a better understanding of space-time means creating a more realistic formal model that takes into account those failures. That's what the practice and also the theory of physics should be based on how exactly our operational definition work and what exactly are we doing in a lab to construct measurement scale. So that's sort of what I wanted to say about time, and I hope this talk sort of gave you some nice idea and things to think about. Thanks for the attention.